Hello everyone interested in magnetic resonance. In this video, I will discuss the Zeeman effect, which is arguably the most fundamental phenomenon in magnetic resonance. As you may know, the Zeeman effect occurs when an electron magnetic moment interacts with a magnetic field. In certain conditions, a similar phenomenon, known as Paschen-Back effect, can also be observed. Here I will try to explain these effects and to provide you a unified perspective on how they could be understood. I will begin my explanation assuming we already know that the operator of the electron's magnetic moment is expressed as a linear combination of the orbital and spin angular momentum operators. This is given by the following formula, in which μb represents the Bohr magneton, and the coefficient Ge is the G-value of a free electron, which is approximately equal to 2, or more precisely to 2.0023. We also know that if we place the electron's spin magnetic moment in an external magnetic field, the resulting interaction can be described by the Hamiltonian, which is a scalar product of the electron magnetic moment with the magnetic field B. Now, the key question is, what does this interaction do to the energy levels of a system containing electron spins? For the sake of demonstration, we will consider an atom as an example of such a system with multiple electrons. As we know, an atom has energy levels, a ground state, and some levels that can be degenerated. In this case, our question can be reformulated as: what happens to the energy levels and quantum mechanical states of an atom when it is placed in an external magnetic field? We will see that the answer to this question strongly depends on the symmetry of interaction within the atom. Okay, let us first describe some general characteristics of the quantum mechanical state of an atom. To do this, I will write down the Hamiltonian for an atom with Z electrons. In the zeroth approximations, it includes the kinetic energy of each electron, the Coulomb attraction to the nucleus, and the electrostatic repulsion between electrons. In a more precise approximation, we also need to include the spin-orbit interaction in the Hamiltonian. This interaction is proportional to the scalar product of the spin and orbital angular momentum operators for each electron. The proportionality factor lambda is determined by the potential in which the atomic electrons move and is given by the following formula. Hence, the total atomic Hamiltonian can be written as the sum of the zero-order term and the term corresponding to the spin-orbit coupling. Regarding the last Hamiltonian, many interesting conclusions can be drawn by analyzing its commutation with angular momentum operators. In our analysis, we consider the total orbital angular momentum operator of all electrons L and its square L square, the total spin angular momentum operator S and its square S square, as well as the total angular momentum J, defined as J equal L plus S and its square J square. I will start with the zeroth order approximation Hamiltonian H0. It possesses spherical symmetry and remains unchanged under rotations. As a consequence, H0 commutes with all angular momentum operators, specifically with all components of L, S, and J, as well as with their squares. This can also be demonstrated explicitly by calculating the corresponding commutators and noting that H0 does not depend on the spin. Moreover, the expectation values of these operators remains constant in time. As an illustrative example, let us consider SZ. Suppose the atom is initially in a state psi, which evolves over the time. According to the rules of quantum mechanics, the expectation value of SZ is given by the following expression. This formula shows that SZ expectation values remains constant as long as H0 commutes with SZ. From general quantum mechanical principles, we know that for commuting operators, it is possible to find a common set of eigenfunctions. In our case, it is important to note that we can choose a basis in which H0, L square, Lz, S square, and Sz are diagonal simultaneously. Due to the high symmetry of an atom, it is expected that some energy levels will be degenerate. However, unlike the hydrogen atom, this degeneracy is partially lifted in multi-electron atoms due to electron-electron repulsion, which breaks the degeneracy associated with the orbital quantum number. Nevertheless, we can consider a basis function corresponding to a specific energy level of our multi-electron atom, and apply to it the operators L square, Lz, S square, Sz to it. Since this basis function is a common eigenfunction for all of these operators, we can assign well-defined eigenvalues L, Ml, S, Ms to it, corresponding to L square, Lz, S square, Sz respectively. Hence, in the zeroth order approximation, a quantum mechanical state of a multi-electron atom can be labeled by the orbital quantum number L, its projection Ml, the spin quantum number S, and its projection Ms. It can also be shown that the degeneracy of a state characterized by specific values of L and S is equal to 2L plus 1 multiplied by 2S plus 1. Having discussed the characteristic of atomic quantum states, we can now proceed to the explanation of the Paschen-Back effect. Let me first recall the interaction Hamiltonian, which describes the coupling between the electron's magnetic moment and external magnetic field, as mentioned earlier. In this context, we assume that the atom is placed in a very strong magnetic field, so strong that magnetic interaction dominates over the spin-orbit interaction. In practical terms, this means a magnetic field is significantly stronger than 10 Tesla. Under this condition, the spin-orbit term can be neglected, and the total Hamiltonian can be approximated as a sum of H0 and H interaction. Nevertheless, H interaction is still much smaller than H0 and is treated as a perturbation. Let us examine what effect this perturbation has on the ground state, characterized by the orbital quantum number L and the spin quantum number S. Since the orbital angular momentum projection Ml can take values from minus L to L with the step 1, and the spin projection Ms can range from minus S to S, and because the unperturbed Hamiltonian H0 eigenvalues do not depend on either Ml or Ms, the ground state is 2L plus 1 multiplied by 2S plus 1 fold degenerate. Our goal is to understand how this degeneracy is lifted by the perturbation H int. According to the perturbation theory, we need to diagonalize H int within their 2L plus 1 by 2S plus 1 dimensional subspace corresponding to the degenerate ground state. This task becomes straightforward if we choose the coordinate system such that z-axis is aligned with the direction of the external magnetic field. This allows me to calculate easily the diagonal elements of each interaction, or in other words, the energy shifts depending on the orbital projection quantum number ml and the spin projection ms. Since our quantum states are also eigenstates of the operators Lz and Sz, E as function of ml and ms can be written as following. The last formula gives us an opportunity to calculate the energies of transitions observed in the Paschen-Back effect when the quantum number ml and ms are changed by 1. Now let us consider the situation where the spin-orbit coupling is stronger than the interaction between the electron magnetic moment and the external magnetic field, yet still much weaker than the main Hamiltonian H0. In this case, we cannot neglect the spin-orbit interaction when studying the effect of H interaction on the atomic energy levels. The influence of the electron magnetic moment interaction with the external magnetic field under these conditions is known as the Zeeman effect. As mentioned earlier, the Hamiltonian of the atom is given by H. We will analyze the eigenstate of H in a way similar to our analysis of H0 above. To begin with, we will examine the commutation relation of H with the angular momentum operators. After performing a straightforward calculation, we will arrive at the following result. Unlike H0, the Hamiltonian H does not commute with the components of L and S. However, it does commute with J and J squared. This implies that the expectation values of Lz and Sz are no longer conserved, and therefore the quantum numbers ml and ms are not good quantum numbers and cannot be used to label the eigenstates of H. On the other hand, the operators H, L square, S square, Jz, and J square all commute with each other. As a result, it is possible to find a common basis for all of them, and we can use the quantum numbers L, S, J, and Mj to label the eigenstates of the Hamiltonian H. According to the rules of angular momentum addition, the value of J can range from L minus S absolute value to L plus S in integer steps. The quantum number Mj varies from -J to J. Now let us take a look at the energy levels of the Hamiltonian H. As we know, they are given by the diagonal elements of H in the basis we constructed above. We can show that this energy do not depend on Mj. To prove this, it is sufficient to show that the energy corresponding to Mj plus 1 is equal to the energy corresponding to Mj. This can be demonstrated using ladder operators. Specifically, the state with quantum number Mj plus 1 can be obtained by applying the raising operator J plus to the state with Mj. Since the ladder operators commute with H, and the product J minus J plus acting on a state alters only its normalization, the energy remains unchanged. Therefore, all states with the same L, S, and J but different Mj values are degenerate. This means that each such state is 2J plus 1-fold degenerate. These considerations give us insight into what happens to the energy level of the unperturbed Hamiltonian H0, characterized by the quantum numbers L and S, which was originally to L plus 1 by 2S plus 1-fold degenerate, when spin-orbit interaction is included. As we can see, this level splits into several sublevels corresponding to different values of J, ranging from L minus S absolute value to L plus S. Each of these sublevels has a degeneracy of 2J plus 1. Interestingly, if we sum the degeneracy of all sublevels, we recover the original degeneracy. As we saw earlier, the electrostatic repulsion between electrons leaves degeneracy with respect to the quantum number L. The spin-orbit interaction leaves the degeneracy with respect to quantum number J. Nevertheless, we are still left with some degeneracy regarding the quantum number Mj. Okay, let us now take a closer look at one of these sublevels, characterized by quantum numbers L, S, and J, and with a degeneracy corresponding to the different possible values of Mj. In atomic spectroscopy, such a state is denoted by the term symbol involving S, L, and J. Now we want to investigate what the interaction with the external magnetic field does to this sublevel. To answer this question, we need to calculate the matrix elements of the interaction Hamiltonian H int within the 2J plus 1 dimensional subspace spanned by the states with different Mj. According to the perturbation theory, diagonalizing this matrix will yield the energy splitting of these states due to the magnetic field. By inserting the expression for H interaction, we can rewrite it in terms of the orbital and spin angular momentum operators L and S. However, unlike in the Paschen-Back regime, we now face a complication. Since L and S do not commute with the Hamiltonian H, the eigenstates L, S, J, and J are not eigenstates of the individual components Lz and Sz. As a result, calculating the matrix element of H interaction in these spaces is not straightforward. To overcome this difficulty, we will employ a useful trick. We express the combination L plus GES as a product of an operator G and the total angular momentum J, with the hope that G can be written in terms of the operators L square, S square, and J square, all of which share the same eigenstates L, S, J, and J. Keeping in mind that J is equal to L plus S and introducing the parameter delta G, which is equal to GE minus 1, we can rewrite the last equation as follows. Now we multiplied both sides of the equation by the operator J. This allows us to express the operator G in the following form, which involves the scalar product of S and J. To evaluate this product, we recall that L is equal to J minus S. Squaring both sides of this equation gives us a relation involving L square, S square, and J square, which can be rearranged to express the product S and J. This gives us the following expression. As we see, we were lucky. The operator G is now expressed via the operators for which the states L, S, J, Mj are the eigenfunctions. Assuming the electron G factor Ge is equal to 2 and using the well-known expression for the eigenvalues of L square, S square, and J square, we can then derive the desired expression for G. Hence, we have shown that the combination L plus GeS is effectively proportional to the total angular momentum operator J. Using this fact, and by aligning the z-axis along the direction of the magnetic field, we can rewrite the matrix elements of H interaction in a simplified form. Since our quantum states are also eigenstates of the operator Jz, all matrix elements become straightforward to compute, resulting in a diagonal matrix. The diagonal elements E, M, J represent the energy level shifts caused by the interaction of the electron magnetic moment with the external magnetic field. These shifts are proportional to the magnetic field strength B, the effective G factor, and to the magnetic quantum number Mj. The energy splitting described here is known also as Zeeman effect.
Here I would like to share some historical background. The Zeeman effect was first observed in 1896 by the Dutch physicist Peter Zeeman. While investigating the influence of magnetic fields on light emitted from a sodium flame, he discovered spectral lines split in the presence of a strong magnetic field. This observation provided key evidence for the interaction between magnetic fields and atomic energy levels. The Paschen-Back effect, discovered in 1921 by Friedrich Paschen and Ernst Bach, is essentially the high-field counterpart of the Zeeman effect, where the magnetic interaction becomes stronger than the spin-orbit coupling. The G factor, which plays a crucial role in describing the splitting of energy levels in a magnetic field, was introduced in the early 1920s by Alfred Landé, a German physicist. His work helped explain the so-called anomalous Zeeman effect and contributed significantly to the development of quantum theory.
In this video lecture above, I have discussed the role of the wave function in the Zeeman interaction. We saw that the symmetry plays a crucial role. However, not all systems exhibit such high degree of symmetry found in isolated atoms, especially when electrons are part of molecules or influenced by interaction with other atoms. Here I would like to demonstrate what kind of effects the symmetry breaking can have. We will see that it leads to the anisotropy in the G factor. This topic is more complex than the previous explanation and may extend beyond the comprehensive scope of this lecture. Therefore, I will omit some derivation in order to use our time more effectively. Okay, let us now consider a hydrogen atom. As we know from quantum mechanics, its energy levels are described by a well-known formula, and its eigenstates are characterized by the three quantum numbers n, l, and m. We will assume that atom is in its first excited state, n equal to. The energy is then given by the formula minus E squared divided by 8 times K times AB, where K is the Coulomb law constant and AB is the Bohr radius. We also know that there are four eigenstates associated with this energy level, determined by the possible values of the quantum number L and M. In this case, L can be either 0 or 1. If we assume L equals to 0, then the total angular momentum of the atom is equal to the electron spin, 1/2. And using the formula obtained above, we obtain G equal 2. If we take L equal 1, then depending on whether the total angular momentum J is equal 1/2 or J is equal 3/2, the G factor becomes 2/3 or 4/3, respectively. We now aim to determine the observed value of the G factor when the symmetry of the interaction is broken. To investigate this, we place the atom in a strong electric field of strength E. As is well known, such a field induces the Stark effect, which partially lifts the degeneracy of the energy level corresponding to the quantum number n equal 2. In the case of Stark effect, the fourfold degenerate level corresponding to n equal 2 splits into the three sublevels as shown in the figure. One level shifts upward, another downward, while the remaining two levels stay unchanged. The energy separation between these sublevels is proportional to the strength of the electric field E. As a result of this partial lifting of degeneracy, we obtain four corresponding orthonormal linear combinations that define the new wave functions. Since these four wave functions, phi1, phi2, phi3, and phi4, are separated by a relatively small energy gap, we will later see that they have a noticeable effect on the interaction between the electron's magnetic moment and the magnetic field. Furthermore, we define spin orbitals by associating a spin state with each wave function. This allows each orbital, in principle, to accommodate two electrons, one with spin up and one with spin down. As a result, we obtained 8 relevant states. It is important to note that the spin orbitals phi2 arrow up and phi2 arrow down correspond to the lowest energy. The material shown above on this slide can be found in the literature. Now I would like to take a step further towards introducing the magnetic field. Since our magnetic field is not going to be very strong, we first need to consider the effect of spin-orbit coupling on the levels already split by the electric field. First of all, it can be shown that the spin-orbit coupling does not lead to additional energy level splitting in the first-order perturbation theory. However, the wave functions themselves do receive first-order correction, which can be later observed through the study of the Zeeman interactions. We assume that the spin-orbit interaction is significantly weaker than the interaction with the electric field. Using the standard perturbation theory formula, we will determine the first-order corrections to the wave functions phi2 up arrow and phi2 down arrow, which corresponds to the lowest energy level in our system. By calculating the relevant matrix elements, we obtain two functions, chi1 and chi2, as the first-order corrections to the wave functions phi2 up arrow and phi2 down arrow, respectively. The coefficient A appearing in these corrections is proportional to the ratio of the spin-orbit coupling energy to the energy associated with the interaction with electric field. Having specified the ground state wave functions, we can now proceed to analyze the interaction between the electron's magnetic moment and the magnetic field. As before, we need to calculate the matrix elements of the interaction Hamiltonian using the obtained corrected wave functions chi1 and chi2. By recalling the explicit expression for the interaction Hamiltonian of the electron's magnetic moment with the magnetic field, we obtain this. In the first order approximation, this yields a 2 by 2 matrix where B plus is defined as Bx plus Iby and B minus is defined as Bx minus Iby. This matrix can conveniently be rearranged as a product of the magnetic field vector B, a tensor, and a vector spin operator. Naturally, the Bohr magneton also appears in this expression. The tensor denoted here by G is commonly referred to in the literature as the g-tensor. We observe that it has different diagonal elements. The components gxx and gyy, which depend on the strength of the spin-orbit coupling and the electric field, are equal. However, gzz differs from them, indicating the presence of anisotropy. In other words, the position of Zeeman interaction energy levels depends on the orientation of the magnetic field, specifically in our case with respect to the electric field. The obtained 2 by 2 matrix of the interaction Hamiltonian can be easily diagonalized. Immediately yielding the Zeeman split energy levels and the corresponding transition frequency. Hence, we have arrived at the final result of this video lecture. To conclude, I would like to summarize the main topics discussed in this video lecture. We saw that when an atom is placed in a strong magnetic field, the Paschen-Back effect is observed, whereas in a weak field, we observe the Zeeman effect. Finally, we demonstrated that the combination of electric and magnetic fields leads to g-tensor anisotropy. The last path, however, was presented rather briefly, so please let me know in the comments what you think about it and whether it was helpful. With this, I would like to finish and invite you to watch my other videos on spin physics and magnetic resonance available on my channel. Thank you for your attention. Bye bye.